Okay, the final topic in Unit 1 to finish out static equilibrium and torque is all about balancing torques. In other words, the final condition for static equilibrium. Okay, the first condition we did for static equilibrium was the fact that forces had to cancel. In other words, net force is equal to 0. Okay, the second condition is what we're going to do here in this lesson, and that is the net torques also have to equal 0. So very quickly, let's just take a look at the whole idea of torque again. The formula for torque is R times F, distance times force. Okay, and D, or distance, or usually written as R in the formula, is radius, or distance from the pivot point. Okay, and then F is the force that's being exerted on the object to try and make it turn. So what we have to do in these questions is we have to try and make the torques balance. In other words, the clockwise torques and the counterclockwise torques have to equal the same thing. They have to add up to the same thing. The sum, in other words, of the torques has to be the same both ways. So, the other thing that you need to remember is that sometimes it's an advantage to put the pivot point in a different place. And what I mean by that is, in a lot of objects, the pivot is obvious, the natural pivot. Like on a seesaw, for example, the pivot is in an obvious place. But we can move that pivot point and call it an imaginary pivot point in order to more easily solve the problem. Okay, and you'll see what I mean by that when we do a couple of these problems in a moment. So let's get right into the problems. Now, these types of problems generally take a little bit longer than just a simple torque calculation, because you may have 2 or even 3 torques in the same calculation. So this one here, for example, we got 2 students balanced on a seesaw. If that's the case, then we've got something that looks like this. Okay, let me just draw a real quick diagram. There's the seesaw. There's a pivot point right in the middle, and by convention we usually draw our pivot as a triangle. Now, you don't have to do that. You can just put a dot there if you want and just label a pivot, but normally if we draw a triangle, that's showing that that's where our pivot point is. Now we've got a student on each end. It says student A is 1.5 meters away from the pivot. So let's say student A is over here, so there's the force of student A. And right here, student B is a little bit heavier, so that student's force is probably going to have to be a little bit closer to the pivot. Okay, and we know that the distance from here to here is 1.5. We don't know the distance there. Now there is another force right here as well that we call the normal force, but because that force is at the pivot, we don't need to worry about it. That's why it's important to know where your pivot point is, because any forces that are exerted at that pivot point do not cause any torque whatsoever. That's the beauty of it. No torque at all. So all we have to do here is we would say that our clockwise torques are equal to our counterclockwise torques, CCW. So remember, torque is R times F. Now if you look carefully at this calculation, look at where A and B are, and you think to yourself, which one would rotate which way? So the easiest way I know to do that is take your pencil, hold it in the middle, and hold it out in front of you, just like it is there, and your pencil represents the seesaw. So if I push down where force A is on the left side, look at the direction your pencil will rotate. And if you're holding it correctly, like I asked you to, just hold it out in front of you with your fingers in the middle holding it. If you push down on the left end, that would cause your pencil to rotate counterclockwise. So RA, FA goes over on that side. And if you push down on the other end of the pencil, the right end, you would get a clockwise rotation. So that means RB, FB would go over here for the clockwise side. Now, in this case, because there's only two forces anyway, it wouldn't matter if you got them mixed up. But if there was more than two forces, then it could matter, because there might be two forces one way and only one the other way. So you'd have to be careful. And we'll see that happening now in the next one that we do. But if we do this, all we do now is plug in our numbers. We do not know what RB equals. We know that force B is going to be the force of gravity for student B, which is going to be 85 times 9.8. Because remember, force is mass times gravity. That's important. That equals RA, which we know is 1.5. That's given. The mass of student A is only 75 kilograms, and we've got 9.80. Now, because we got the 9.80 in both terms, if we want, we can actually cancel them. We don't have to, but hey, why not? If you can do it, it simplifies things a little bit. I divide by 85 on both sides, and my 85 and my 85 are gone there now. So now the only thing left on the left side is RB. So I've got RB is equal to, and it works out to be approximately 1.3 meters, which is choice C. Choice C. Now, that is a fairly straightforward one. That would be what we call a level 2 question. But it's a fairly straightforward level 2 because there's only two torques. Okay, one thing to find. The pivot point is pretty obvious, so that's a pretty straightforward question when it comes to torque calculation. The next one is a little bit more challenging. And again, I would always encourage you to draw a little diagram. Okay, I always tend to draw diagrams of these situations. So let's draw the diagram down here. Here is the beam, and it's supported by a rope at each end. So in other words, I got a rope right here that's providing a force, and I got a rope right here that's providing a force. Okay, so we're going to call those ends left and right. So I'm going to write in force left and force to the right. Now, then it says the mass, or the weight of the beam, sorry, is 1.0 times 10 to the 2. And when you do force of gravity, the force of gravity is always at the center of gravity, or the center of mass. So that would be right there. That's what we call the force of the beam. I'm going to call it FB, B for beam. That's the force of the beam, the force of gravity for the beam. But there's also a person sitting 2 meters from the left end. So in other words, we got a person sitting right here somewhere, and we're going to call that force FP, P for person. Now you can call them anything you like. You can call them A and B, you can call them force 1 and force 2. It really doesn't matter. Okay, whatever keeps it clearer in your head. I tend to use letters that represent what they are, because that generally makes it a little easier sometimes to keep things straight. But if you want to call them forces 1, 2, 3, and 4, that's fine too. It's entirely up to you. So we tackle that one exactly the same way. The clockwise torques and the counterclockwise torques have to be equal. Okay, that's the only way for that beam to stay still. In other words, be in static equilibrium. And we always assume that's the case unless it tells us otherwise. So the clockwise torques. Well, first of all, we got a problem. We know what this force is. We know what this force is, but we don't know the left or the right force. But I'm trying to find the one on the right. This is the one I'm trying to find over here. So somehow I need to get rid of that guy right there. And that's easy to do because all I got to do for my torque calculation is I put my pivot where that force is. So if I put my pivot right there at the left end, then that eliminates the left-hand rope from the torque problem because there is no torque at the pivot. So that eliminates that one from the calculation completely. So let's do the rest. Now, clockwise. If I look at that, if I hold my pencil like that where the pivot is, right on the left end, any force that pulls down on the pencil is going to cause a clockwise rotation. So that means both force P and force B are both clockwise torques. So I say RP FP plus RB FB. I add the two of those together because both of those are clockwise torques. And that will equal the counterclockwise torque, which is the only other force left, which is the force on the right, which pulls up on your pencil. Remember, holding your pencil out to determine the directions. So if you pull up on the right-hand side, that would be a counterclockwise rotation. So that radius on the right and the force on the right, that would be your counterclockwise. Now you notice I didn't put any angles in, because if you look at every single one of these forces, every one of them has a right angle. So they're all 90 degrees. So I just left out the sign of 90 just to save space. Okay, RP. Force P, the force of the person, it says he's 2 meters from the left end of the beam, which is where we got our pivot point. So he's 2 meters away from the pivot. So I put 2.0. The force of the person is 4.0 times 10 to the 2. I'm going to write that as 400, which is easier to punch into the calculator. Plus, I've got radius for the beam. The center of gravity of that beam is right in the middle of the beam. That means that it is halfway from the end. And if the beam is 10 meters long, half of that is 5. Because it's 10 right from one end to the other. So halfway is 5. So this force right here, for example, that's 2.0. This one right here is 5.0. And this one right here is 10.0. Okay, that's where all the forces are located. Anyway, the force of the beam is 100 newtons, and on the other side, the last force over, the one right over on the very far right, is 10 meters from the pivot, 10.0, and the force on the right we do not know. So if I want to get that force on the right all by its lonesome, I would divide both sides by 10. That would cancel those out, and the force on the right would work out to be 130 newtons, which is, in scientific notation, 1.3 times 10 to the 2. So there's a couple of pretty typical torque problems. But we're going to look at a number of these just to make sure you got the hang of it. Let's try this one. This time we've got a ladder. Now, ladders can be tricky because ladders have angles in them. So for this ladder, the torque for the person at this point Q, remember, for a person standing on the ladder, the force would be the force of gravity straight down. So there's our force. There's your force right there. Now what that means is, now we got to figure out what this angle is right here. But that's actually pretty easy because that angle down there is the same as this angle right here. And that's easy to figure out because the wall is perpendicular to the ground, so therefore that's 90. So we got 60, we got 90, that's 150. And remember that the three angles of a triangle have to add up to 180. So that would make this a 30-degree angle right there. 30 degrees, which means this one here is also 30 degrees. So now we can figure out the torque. The torque is RF sine theta. And remember, theta is always the angle between the force vector and the object, which in this case is a ladder. Now, this is not a conservation of torque or a net torque thing. This is only asking us to find one torque, the torque produced by the person. So let's work it out. He's 3 meters up the ladder. So if the pivot is at the bottom, which is the logical place to put it, we put 3.0. The force is the mass of the person times 9.8. And then I say sine of 30. And the answer to to that calculation, okay, the answer to that calculation would be 956 Newton meters. So obviously the answer is either C or D. So I can forget these two, because 9.6 times 10 to the 2, that's what that number would work out to be. Okay? Now we got to worry about the direction. So use the old trick with the pencil. Hold it up so it makes the same angle as the ladder. Grip it at the bottom, and then pull down at the point Q. Pull straight down, and your ladder would start to rotate clockwise, which tells you the correct answer is C. Correct answer is C. And we're done. Okay, so that one could be a little tricky. When you're dealing with ladders, you really got to be careful with the angles, but the rest of it, not bad at all. Not too bad at all. Let's try another one. This time we got no angles. We got a uniform plank that's 16 meters long. It weighs 350 newtons, 3.5 times 10 to the 2. And there's supports at each end. Now let's do our diagram again. I've got a force at this end, and I've got a force at this end. So essentially what I have is a force on the left and a force on the right. Okay, but since that's labeled A, I'm going to call this force A. Now, I've got another force where the man is, and it tells me that this person, I'm saying there's a man because he looks like a man in the picture, but he's standing right in the middle of the plank, right there. And there's another force there too, because the force of the person and the force of the plank are both in the middle in this case, because the person is standing in the middle. The center of mass for the plank is also in the middle, so I'm going to call that FP. FP, because it's the force of the person and the plank. So I'm going to say P for person plus PL for plank. Both of them together. And this one over here, that's going to be F R for right. Now, the thing is though, I got two unknowns. I don't know FA, but I'm trying to find FA. That's what it's asking me for, that normal force at point A. So I don't want this one over here. So what I do, in order to get rid of that one, is I put my pivot right where that force is located. And that gets rid of it. Now it's gone. Okay, I don't have to worry about it now for torque. So now I can say clockwise torque is equal to counterclockwise torque. And clockwise torque equals counterclockwise torque. All I got to do now is figure out which one is clockwise, which one is counterclockwise, because there's really only two forces there I have to worry about. And if you grip your pencil now at the right end and push up, that would give you a clockwise rotation. So in other words, RA times FA, that's your clockwise. Your counterclockwise is the other one, the person and the plank. So in other words, I'm going to say P plus PL. And the reason I can combine them like that is because they're both in the same location. If they weren't, I'd have to keep them separate. That's the only reason I'm doing it this way. So let's put in our numbers. I know how far it is from the pivot point, which is right here, remember, at this end over here, to the middle, because it's halfway. In other words, it's 8.0. And all the way to the other end, that's 16.0. So that gives me the two radii for those two forces. So RA is actually 16. FA we don't know yet. Okay, the distance to where the plank and the person are standing, that would be 8.0. And the force for both of those, all I can do is add them together. The person is 850 newtons. The plank is another 350 newtons. And there's your setup. Divide by 16 and I will get the force by itself. So force cancels here and here, and I've got FA equals. And if I did that calculation, I would get an answer of 600 newtons. which becomes 6.0 times 10 to the 2 newtons when you put it in scientific notation, because that's the way all the answers are given for this one. All right, moving on. Let's try another one. Okay, and all of these are done exactly the same way. Okay, when there's no diagram given, it's always helpful to draw one. So here's our lever. The lever is 5 meters long, it says. And it says we got an object or a force at one end. So here's a force at one end of the lever, right here. We'll just call that a force. Okay, and we've got an object on the other end. So that's another force. That's going to be like a force of gravity. We'll call that one. That's the force of gravity on the object. Looks like this. Force of gravity on the object. And the pivot is right here. Pivot is right here. 1 meter from the pivot point. 1 meter from the pivot point. Okay, so what we have to do then next is figure out what the distances are. Let's figure out the distances. Well, it tells us that the object at the end is 1 meter from the pivot point, so this force here is 1 meter. And because the lever is 5 meters long, then we know the other force has to be 4 meters away, 4.00. So we know our two distances. We know our force over here is actually 4,000 because it's 4.00 times 10 to the power of 3. So all I've got to do now is figure out the maximum weight that would balance. In other words, what would Fg be on the other end there? So all you got to do now is plug in your numbers. So here's what we got. Remember, clockwise torque equals counterclockwise torque, so I'm not going to write that in again. I'm just going to write it like this. The clockwise one is just the RF, the one with no letters on it. And that would have to equal the counterclockwise one, which is RGFG, the force of gravity on the object. And we know all of these values except for one. We know that the R here is 4.00. The F is 4,000, which is really 4.00 times 10 to the 3, because all these numbers you'll notice have 3 sig figs. And then we've got RG on the other side is 1.00, and the FG we don't know. So divide by 1.00, which is really not going to change anything, and we get Fg is equal to 16,000, which is actually going to be C, right there. Okay, so all of these you can see are basically the same thing. They're basically the same questions over and over again. Okay, let's do the next one. Now we've got a bridge. And again, the forces for the most part are given. This is force A right here. It didn't come out very good here when I copied it from the public, but this is force B at this end. These are the distances, 6.0 right there, and 14.0 right there, meters and meters. And we got A and B on the two ends. So we've got two other forces that are not actually shown. We've got the force for the car, or the truck in this case, which we'll call Ft. And we've got the force of the bridge itself, which we'll call Fb. Fb. B for bridge. Okay, actually I can't really say B for bridge, can I? Because I already got an FB there, so I'm going to say BR. BR. Now all you got to do is figure out which ones are clockwise, which ones are counterclockwise. So where's your pivot going to be is the question. We want to know the upward force at support B. So in other words, we're trying to find this guy right here. So it's no good to put your pivot there. That's not going to help. That would eliminate that force from your calculation. So we're going to put it at the opposite end instead. We're going to put the pivot right over here at this end. There's our pivot. Put the pivot at A. So if we do that, that would make Ft and F bridge your clockwise torques. Your clockwise torques. So RT, Ft plus R bridge, F bridge, okay, would have to equal, the only other force is FB, so I'd say RB, FB. And the only thing left to do now is put in your numbers. Well, the FT is pretty obvious because the distance is actually shown on the diagram. It's 6. The force of the truck is going to be the mass of the truck, which is 2,000 kilograms, times 9.8. Okay, when the mass is given in kilograms like that, don't forget to multiply it by 9.8 to turn it into a force. You have to turn it into a force. Plus the distance for the bridge. Well, the bridge, you can see, is 20 meters long. So halfway, which is where the center of mass always is in these uniform objects, is going to be 10. The mass of the bridge is 8,000 kilograms, and we have to multiply that by 9.8. And then that has equal to the distance for force B is all the way right to the other end of the bridge away from the pivot, which is 20 meters away, times FB. So you just divide both sides by 20. And when you do that, you get the force for the bridge, FB, would equal 45,080 newtons. So again, in scientific notation, that would be this number right here. 4.5 times 10 to the power of 4. Now, the other thing you got to watch for, if you had forgotten about these 9.8s, you would have gotten this answer right here, look, if you forgot the G. So, again, a reminder that you need to make sure you don't make those common mistakes, because those answers are there, unfortunately. Those answers are always there. Okay, so that's the way that one works. Okay, one more page of multiple choice, and then we're going to take a look at some what they call constructed response, or in other words, long answer questions. All right, let's try this one. We got a boy and a girl trying to balance a seesaw, and if the girl sits at one end, so let's say that the two torques got to balance. So I'm going to say R for boy times force for the boy would have to equal R for the girl times the force for the girl. And again, because force of gravity is straight down and the seesaw we're going to assume is level, the angle is always going to be perpendicular for these. So RB, for the boy, we don't know that distance. That's what we're trying to find. The force for the boy would be 45 kilograms times 9.8. On the other side, the distance for the girl, well, she's at one end of the seesaw. Assuming that the pivot is in the middle, then she would have to be 1.5 meters because it was a 3-meter seesaw. So a pivot in the middle would mean the girl is sitting 1.5 meters from the end. The mass of the girl is 35, and G is 9.8. Now, if you like, the G's will cancel, so you can do that if you want. And at the same time, we would divide by 45 on both sides of this equation, and that would cancel out the 45s here as well, and that would leave me with RB, or the distance of the boy from the pivot, would be 1.5 times 35 divided by 45, and that answer would be this. Oops, circle in black. Choice A. Choice A. Now, last multiple choice, and then we'll look at some long answers. Last multiple choice. Okay, so for this one, we're asked first of all, what is the tension in this cable if we have a 490 Newton object suspended from the end of a 5-meter long beam? We're going to assume the beam is massless. So what that means is there's no force of gravity for the beam. So that means there's only two forces. There's this force right here, which is the force of gravity, and there's this force right here, which is the force of tension. Tension in the cable. So there's only two forces. The force of gravity for the beam itself doesn't exist. And the reason it doesn't exist is because it tells us to assume the beam is massless. Or at least that the mass of the beam is so small that it doesn't have any impact. And that's usually what we mean. Sometimes it'll say assume the mass of the beam is negligible. That's another way of saying the same thing. No such thing, obviously, as a massless object, but sometimes the mass can be so small that it doesn't really affect the outcome of the problem. Anyway, if you look at this, the pivot is right here at the hinge. Okay, that one is pretty obvious. There's our pivot point. We'll draw a triangle there. So we measure our distances from the pivot. So the clockwise one here is tension. So I'm going to say RT, force T, force of tension. And there's an angle there, so I'm going to say sine theta T. That has to equal the other one, which is RG, FG. And if you want to say sine theta, you can, but you don't have to there because that one is perpendicular. And the sine of 90, like I've said several times in this session already, is equal to 1. So you don't actually have to include it in the calculation there if you don't want to. So here's what we do. RT. We know the distance is 5.0. The force of tension we don't know, but we also know that sine of 40 is the angle. Okay, RG. The distance to the end is again 5.0, and the force of gravity there is 490. Now, if you want, you can cancel out these two distances. So what it turns out there that the length of that beam doesn't even matter because you're not given the force of the beam. So sometimes they may not even give you the length of the beam in this situation. That would make it a level 3 question. But it's still doable. It's doable because the distances are going to cancel out anyway. The R's cancel, so it's not going to make any difference in this situation. Both the R's are the same. So divide by sine, 40 on both sides, and you will get 762 is the force of tension, which rounds off to 760 newtons, or C. And that concludes the multiple choice for this topic. Let's look at some long answer questions, or as they're called on the public exam in Part 2, constructed response questions. So here's our first one. Very similar to the one we just did, only this time we do have a mass of the beam or of the rod. Okay, so that makes it a little bit different. So the first thing you should always do in a case like this is draw a diagram. This diagram shows all the forces acting on that object. So we've got the tension right here. There's your tension. That comes from the wire, from the cable, holding it up. Then you've got the force of gravity for the block. I just call that FB, or FS for sine, whatever. Then you've got the force of gravity for the rod itself. And then finally, you've got a force being exerted in this way a little bit by the hinge itself. A force by the hinge itself. That's going to be the pivot point, however. So because that's the pivot point, we don't even need to worry about that force right there. That's not going to be part of our calculation at all. And the reason we do that is because the force we're asked to find is this one. So we don't want to cancel that one out. So obviously we're going to put our pivot point here at the other end. Now if we were asked to find the force of the hinge, then we go back and put the pivot at the other end. Okay, because it really doesn't matter where you put your pivot. You put it wherever is the most, or the biggest advantage, the most advantageous. So anyway, the next thing you do, if the hinge is the pivot point, you'd say net torque is 0, or in other words, clockwise equals counterclockwise. Now the person who did the solutions for this particular exam did it the other way around. Okay, so the counterclockwise would be the tension. That's what would cause the counterclockwise rotation, whereas the rod and the block would cause the clockwise rotation if it were allowed to rotate. Okay, so plugging in those numbers, the only one that we need an angle on is the tension. That's why you see T sine theta R. And normally the R goes first, but when you're multiplying the order, it's not important, so that's why it's done this way. And the reason they said R over 2 right here, this one here, is because for the rod, remember, it's right in the middle. So whatever that distance is right to the end, this is right in the middle. So it's halfway. So you plug in those numbers then. Here's the numbers. So T equals, there's your calculation, and you get 78 newtons of tension in that wire. That's the magnitude. Okay, so that's a pretty standard question for balancing torques. There's almost always some kind of balance torque problem on your public exam. It's there just about every time. So be ready for it. Here's a very similar situation. Now this one would be more of a level 3 question. So we got a 1.5 kilogram rat is walking out on that beam that's 2.2 meters long. He's trying to reach a food basket right here at the very end. Now this cord that's holding it up can only withstand a maximum tension of 45.5 newtons. We want to know how far can the rat walk out, maybe he can make it to the end, but how far can he go before the beam breaks? How far can he go before it breaks? So let's draw a diagram. Here's our beam. The forces on that beam are tension right here. We've got the force of gravity for the basket right here. We've got the force of gravity for the beam right in the middle, right here. And we've got the force for the rat right here. We're not sure how far he gets, so I'll just put it right there just for argument's sake. And we've got the force of the hinge right here. So let's label those. This is the force, I'm going to call it H for hinge. This one here is force of gravity for the beam. All right, this one here is force of gravity for the rat, and this one here is force of gravity for the food. So then you set up your equation, and your equation would start out clockwise torques equal counterclockwise torques, as they always do. So the only clockwise one, and actually this is reversed here, because if I put the pivot right here, which is where I need to put the pivot, because I want to eliminate that force from our calculation, okay, then this would actually be reversed. So this would be the counterclockwise, this would be the clockwise right here. Okay, the force of tension, in other words, the force in the cord, would be the counterclockwise. The other three would be the clockwise ones. Then you plug your numbers in. Okay, and you notice they put the sine theta in all the places. You don't have to do that. Like I said, the only one that it really matters for is this one here. This is the only one that actually has an angle in the ones that we're calculating there, the tension itself. Okay, then you do this, plug your numbers in, and remember now, the one that you don't know is for the rat, which was the first one over here on this side. See, there's your unknown. So this R here you don't know. That's why we leave it in right there. See that? But we know all the forces because they're all forces of gravity except for the tension in the cord, which was given as 45.5. So that's the tension in the cord, force of tension. And the 2.2 meters, because the cord is attached all the way over at the other end, that's where that comes from. And then sine of 45, that's the angle between the beam and the cord. So that looks after the counterclockwise. And on the other side for the clockwise, that's the force of gravity for the rat. It's just the mass of the rat, which is 1.5 times 9.8. Then we've got the beam itself, which is 1.1, right? Because the center of gravity is the center of the beam. That's where the force is located. So 1.1 times 19.6, which is just 2.0 kilograms times 9.80. And then finally, the food basket at the end, which has a mass of 1.3 kilograms times 9.80 to get 12.7 newtons, and it's 2.2 meters away. So plug all that in, solve for R, and you will get R equals 1.46. So obviously he doesn't get all the way. He will get to approximately where I drew the diagram right here. So before he gets to the end where the food basket is, the cord will break, the rat will fall, so will the food. So I guess eventually he'll get the food because the food will end up on the ground and so will he. But he can't get to the end without the cord breaking. That's the important thing. Okay, here's another one. This is a ladder problem. We want to know what force does the wall exert on the ladder. Well, let's take a look. I'm going to put the pivot point down here because that eliminates the force the ground exerts on the ladder, which might be up this way, right? This is the force of the ground. Here's the force of the ladder. Here's the force of the person. And here's the force of the wall. Those are all the forces that we need to worry about. So we do our clockwise equals counterclockwise. So the wall itself is the counterclockwise torque, and the ladder and the person are the two clockwise torques. So they go together. We plug your numbers in. Now, you got to be careful with angles here now. You'll notice that they used sine of 71 for the wall because the angle at the bottom here was 71 degrees, which means this angle up here is the same. Now, then you'll notice that they went cosine 71. Now, instead of doing that, we could have said sine of 19. That's the same thing. That's the way I would normally do it because we normally say RF sine theta for torque. So I'd say sine of 19 instead of cosine of 71. But it doesn't matter because both of those calculations give you exactly the same answer anyway. So it really doesn't matter. The reason this one is 3 right here is because that's how far from the bottom the person is standing. The reason this one here is 2.5 is because the force of the ladder is at the center of mass, which is halfway up the ladder. And that's 5 meters for the length of the ladder, which means 2.5 meters for the force. And when you work the rest of that out, you get the force of the wall is 143 newtons, or 1.4 times 10 to the 2, because you're really only allowed to have 2 sig figs. But this particular one didn't grade for significant digits in units. So that's the way that one works. So like I said, all these are basically done the same way. Now this one asks you for the force at each end. So what you have to do, the diagram is already drawn. So I need to pick a side first. So what we're going to do is we're going to put our pivot right here first. And that will allow us to find F2. Okay, so you can see what's done there. F2 times 2, or 2 times F2, whichever way you want to look at it. That's our F. Okay, then we've got 75 times 9.80. That's the mass of the box times 9.80, which is gravity. And then we've got 2 take away 0.6. And the reason we do that is because the beam is 2 meters long, and the box is 0.6 meters from the end. So that's 1.4 meters. And that's where all the measurements come from. The 1.0 meters is because that's the center of the table. That's the center of the table. Okay, and when we solve that, we get F2 equals 637 newtons. Now, once you know what F2 is, now you got a choice. If you want, you can take your pivot and move it to the other side and find F1 that way, or you can use the fact that F net equals 0 to find F1. So in other words, the forces up, which is force 1 plus force 2, equals the forces down, which is the table plus the box. And you know all those now except for 1, and that gives you an answer of 343 newtons, or 3.4 times 10 to the 2 if you want 2 sig figs. Okay, so that's the way you do that one. Now, like I said, if you wanted to, you could have moved your pivot from the left side to the right side, put your pivot there, and done the torque again. Okay, both will work. You would have gotten exactly the same answer doing it that way. It just would have changed a couple of your distances, that's all. Okay, one last question, and then we'll call this topic done. We've got a 20 kilogram sign at the end of a 2.5 meter horizontal beam hinged to a pole, and we've got a tension in the cable. So we've already done one essentially just like that. So we've got a number of forces. We've got tension there. We've got force of gravity there. We've got the force of the beam right there. We'll call that one FB. We'll call this one FS for sine, and we'll call this one T, or FT for force of tension. So there's your diagram. Then you'd use the idea that clockwise equals counterclockwise, and they've done it a slightly different way there. Okay, they worked out all the torques first. The only one you couldn't actually completely work out was the cable. That's why the T is still in there. And then you use the idea that clockwise equals counterclockwise, so you put them all together, put your numbers in, and you end up with a tension of 456 newtons. Remember, clockwise equals counterclockwise. So the two clockwise ones were this force and this force. They were clockwise. This guy here was counterclockwise. So that's why it worked out like that. So that's the magnitude of the tension in the cable. And then the second part of this question asked you to find something else. Take a look. This one asks you to calculate the magnitude of the horizontal component of the force exerted on the beam by the hinge. So remember, there's a force right here, like that. Now we don't know what that force is, but we do know that it has a horizontal component and a vertical component. So we have an Fx and we have an Fy, Fx and Fy, horizontal and vertical. So all we got to do is remember that the vertical forces have to cancel and the horizontal forces have to cancel. So because in the second part of this question we're asked for the horizontal part of that, all we got to do is say this, that Fh equals T cosine theta, which means Fh equals 344. And the reason for that is because the forces to the right had to equal the forces to the left. Okay, forces right, which is the horizontal component of the hinge, have to equal the forces left, because the only other force was the horizontal component of our tension. So that's why we have to do it that way. So the force right was Fh, the force left was T cosine theta, or in other words, the horizontal component of our tension. And when we work that out, there's the answer that we get. That sums up the idea of balancing torques. So the only thing you got to watch for sometimes in these is which forces are clockwise, which ones are counterclockwise, and also be careful with your angles. Sometimes there's an angle between the force and the object. It doesn't matter if the force is perpendicular with the ground. It's with the object that's important. That's where you always measure your angles from. Okay, so if the force is pointing down towards the ground and the object is parallel, then that would be a right angle. But if the force is pointing down to the ground like gravity always does, but the object is a ladder leaning up against the wall, then the force does make an angle with the object. So watch for that, please. And that finishes off Unit 1. Okay, Unit 1 is now complete. So later on, the next set of topics are going to deal with Unit 2, which is all about electricity and magnetism. So we'll start that later in the week. So again, good luck with your studies. Work hard, and be sure to join us for